through a dual pole workshop here. So Paul had worked quite closely with Don Burgess and those guys in Norman, but now Paul is back at Weather Service headquarters, and he's there on a permanent basis now. So I'd like to give you just a little bit of a background on Paul, and then he'll start with the workshop. So let's take a look at that video.
Yeah, that's fine. That's fine.
There's no audio actually streaming, so we'll play this again, but we'll just come out and dissolve to you. You guys want to see that? Oh, right.
Sure.
Let me just ask you this too, Paul. When somebody asks a question, if you could repeat the question just to make sure the online viewers can understand what the question is. Thank you very much.
So I'm good to get started?
Yeah. So go ahead.
Yeah, so that was, so I work at National Weather Service headquarters now, kind of an executive advisor to the director of the Weather Service, Dr. Jack Hayes. I'm sure all of you heard of who that is. But for 8 years prior to going to headquarters, I was in radar training, and obviously I relish any chance I get to be able to come back and look at radar images and discuss them with all of you. So what are we doing with this workshop? We're essentially going to play a game of what is that? And by that I mean we're gonna identify, using the dual pole radar products, what it is that it's showing, and then hopefully get a short discussions going on how that might improve all of your jobs as broadcasters, and in general, all meteorologists across the country. So I'm building off kind of what Don Burgess briefed you earlier. I'm going to make this pretty interactive. I'm probably going to call some of you up to at least point at some stuff. So be aware of that. And obviously, I really hope you guys volunteer to do that kind of stuff too. Now, the hard copy of the decision aid that Dave passed around, we can use that as a decision aid, and we'll go through that a little bit. I also tweeted, if you don't want to use a hard copy, you'd rather just go online and use a PDF version, I tweeted the location of that exact same document in electronic format. So we're going to apply techniques. All I've got are radar images. I've got roughly, I think, 13 or 14 different events all across the country from the upgraded dual pole radars. And so we'll apply techniques on how to understand how dual polarization would benefit those types of events in that part of the country. And then finally, ultimately the goal in the Weather Service, and also I'm sure the goal with all of you, is why are we even doing dual pole? Really, the benefits are it really conveys a much more confident message to your viewers from the Weather Service perspective a more confident message to our customers, the general public, emergency management, that we're much more sure about what the radar is showing and are able to convey that in our messages, particularly warning messages. So how are we going to do this? For each event that I'm going to go through, we will do, I'll give just a really brief background on what type of event you should be expecting. Because we're here to view radar images. I'm not going to go into the weather background of each event. And then I'll show a series of radar images. I'll kind of go through the methodology of how a weather service forecaster would do it, and hopefully that you kind of see how one would properly interpret dual polarization. Use the decision aid. So we'll use that to hopefully identify what type of precipitation or non-precipitation we're looking at. We'll discuss the most likely type and then kind of review what the correct answer might be. So jumping right in, the first case we're going to look at comes from Wichita, Kansas. It was on November 9th. I don't need to discuss the sounding too much, but it's kind of a typical snow sounding. So really, forecasters going into this event, they knew they were going to start off with rain because surface temperatures were in the 40s. And then, as the cold air deepened from the north, they were expecting it to change over at some point. The trick is when and where is that changeover going to occur? It's kind of tough with computer models to nail that down to within an hour. I'll show you with dual polarization, you can nail it down to the minute and also the location of where it's changing over. So their surface observations, Wichita is right in this area here. Notice that at this particular time, it's late in the evening on the 9th, low to mid 40s temperatures. Upstream, it's upper 30s, and they're still reporting rain just about everywhere. Just showing a velocity image just to show you that, hey, the radar isn't going to change. Reflectivity and velocity are still going to be there with dual polarization. But notice nice northerly flow with the green inbounds and the red outbounds. Northerly flow just about at all heights. So here's your reflectivity image, just to give you bearings. So the radar's here, Wichita. The bulk of the metro area is right in that area. And so here's this massive batch of precipitation moving from northwest to southeast. So on this particular image, kind of focusing on, okay, there's moderate, with reflectivity, you know there's moderate precipitation going on in all these batches, but what is it? Is it rain? Is it snow? Is it a mix? With reflectivity, there's no way you're going to know. So let's look at, this is differential reflectivity. And one of the things to keep in mind with differential reflectivity, strong positive values, so greens, yellows, reds, almost always going to be larger raindrops or liquid precipitation. When you get down towards zero, the types of things that Don had mentioned and that I'll reiterate, get down near zero, probably hail, could be really tiny raindrops or drizzle, or snow. Those are the three type of options to think about. So let me toggle between the two. So notice this heavy batch of precipitation on top of I-35. It's got higher differential reflectivity. So in your decision aid, take a look at the differential reflectivity page. Does it mention what values above 2 kind of signify?
Which one?
Let's see, does it have it on there?
We have the different precipitation.
All right, let's do light to moderate rain. So we've got 30 to 40 dBz reflectivity and differential reflectivity between 2 and 4. Does that match up pretty well with light to moderate rain on everyone's chart? Roughly? And then we'll get to it in a little bit, but so just behind this batch, so note this whole area here to the northwest. Yes, reflectivity values are similar, but notice that differential reflectivity is effectively 0. It's between 0 and about plus 0.2, that really dark blue value. And so we'll get to what it is in just a second. The final piece of the puzzle to help determine precipitation type is this correlation coefficient. And the easiest thing to think about is when it's magenta, that's values above roughly 0.97, 0.98. There's only 2 things that could possibly be. It's either all rain or all snow. Nothing else. Anytime you see magenta on this particular image, it's either all rain or all snow. It can't really be anything else. When you see values drop into the yellow range, which is around 0.9, that's a mixture of precipitation, whether it be rain, hail, or rain and snow. It's a winter event, so we can rule out rain, hail, right? So where it's decreased in the yellows, it's a rain-hail mixture. Out here, it's either all rain or all snow. We're not quite sure which at this particular time until we go back to here. Now, with differential reflectivity down around 0, strong enough reflectivity, and then correlation coefficient of 0.99, so it's either all rain or all snow. What does everyone think makes the most sense? Is that all rain or all snow in this area?
Probably snow because of the area of transition.
You got it. So he just touched upon where the human forecaster makes a huge benefit here. We know that where the radar beam's traveling, this is the closest to the ground, closest to the radar, closest to the ground. So obviously, in this type of setup, closer to the ground is where your melting is going to occur. So you're seeing melting kind of in this 1,000 to 3,000 foot band is turning into rain there. Everywhere outside of that is turning into snow. So it is a little tricky figuring out, yes, it's all snow here. So what's happening at the ground? There's still 2,000 to 3,000 feet for this to fall through before it hits the ground out there. So that's always going to be a problem with dual polarization. You know what it is at the radar beam. It's all snow. Below that, it's kind of tricky. You do know that it is melting closer to the radar in the lowest few thousand feet. So let's go. A good way to do this is to look at a higher elevation angle, just to see if there's a little bit better agreement of what's actually going on. And so again, remember, magenta means what? What does magenta mean? All rain or all snow. And then if you're into the yellows, what does that mean? Mixed. It's rain snow mix. So even at this, so we're looking at a 1.5 tilt. So this is looking a little bit higher up. We're still seeing kind of a band of melting. So inside the melting would be rain. Outside that, all snow. Let's fast forward just a couple hours here. So what's happened? Now, one of the sites, I think that's McPherson or Hutchinson. I always forget. Hutch. They are reporting snow, 34 degrees. Temperature in Wichita has dropped to 38 with light rain. So the cold air has deepened a little bit. Now look at the reflectivity image. Using reflectivity, we know that there is heavy precipitation here and kind of in these bands up to 40, 45 dBz. But still, we don't know what it is. Now the nice thing is it's right on top of Wichita. So we're only a few hundred feet off the ground. So there's almost without a shadow of a doubt, dual pole, whatever dual pole says is here, 100 feet, 200 feet off the ground, that's hitting the ground. So is it going to be rain? Is it going to be snow? Let's take a look. Look at this little band right here. This is right on top of, what is that, 235 or 135? Oh. It's all rain or all snow, right? Little pocket here too, right? Just east on I-35 there, out here. Yep, has to be snow. When we can look aloft to verify it. So what you do is you'd look aloft, see in this little column if there's any melting going on just above that. Turns out there's not. So in this pocket, in this part of Wichita, you're identifying all snow, and it's actually pretty good snow. We're talking 40 dBz. Those really heavy, kind of big, half-dollar size flakes going on. Out here, same deal. It's about 900 feet off the ground here. Chances are that snow is reaching the ground as all snow. Even without, and of course, any type of viewers you have out there or spotters that are tweeting these things will be able to help identify, yeah, it's snowing here. And then you kind of know that all around there, heavy snow's going on. So toggling between these two again. So there is still some cases of a rain-snow mixture over Wichita. You notice it's in that yellow range, rain-snow mix, right in that area. And then kind of the clincher, that same band that was really heavy, it's right around 0 to 0.2. So on your snow chart, go to your snow chart. We'll kind of look at that a little bit.
Wet snow or dry snow?
Yeah, we'll have to go to dry snow. And here's where it's kind of tricky. I'll explain. So each page was split up by how the algorithm that Don talked about, hydrometeor classification, how the algorithm tries to figure out what precipitation type is. But to you and me as humans, wet snow means something totally different than what the algorithm's finding out. This snow here to the algorithm would be called dry snow if it was able to detect it. In reality, though, the algorithm wasn't able to detect the snow here. It thought it was all rain. But to you and me as humans, we think wet snow is that really, the stuff that's great for making snowballs, right? Really, really wet snowmen, snowballs, those kind of things. To the hydrometeor classification, wet snow is a rain-snow mix. So it's one of the other reasons why I firmly believe a trained human can beat the algorithms with dual pole all the time in any situation. Just been able to determine what is really wet snow. So that's really just wet snow that's all wet snow, not mixed with any rain in that band just north of the radar and on the northwest side of Wichita. We go a little bit further now, and notice how high the reflectivity got there. Again, before dual polarization, I'm not sure that you'd say that that was snow. I mean, how many times do you see 50 dBz snow? Nor'easters, I'm sure you can see that occasionally, but again, high correlation. You see the batches of all snow, and we'll verify all snow with the next product, but just little batches east of the radar, and then there's still some rain snow mixed in different parts of the metro. So all over the metro, you're getting either all snow or then a rain snow mix. Here, again, here's the thing that really verifies it. When it drops off to near zero, that's snow. When it gets higher, it's a rain snow mix. So I'll let you look at that just a little bit longer. So the nice thing is, if you have a radar located near a major metro area, which a lot of the 88Ds are, you are able to get this kind of resolution on where the rain and snow is falling across the metro area. Because you're only a few hundred feet off the ground with the radar. Chances are it's not going to change very much in those few hundred feet, particularly when you're talking really heavy stuff falling. Looking, I think this is just a little bit later, maybe a half hour later, just showing the evolution. At this particular time, there's only a few areas of melting that are still occurring. Everywhere else, it's turned completely over to snow. And again, how do we know that? Right here. As long as you've got the higher values mean rain snow, everywhere else where it's kind of that blue color near zero, it's turned over to snow everywhere. So towards the tail end of the event, we're changing over to snow entirely. Oh, you can't see that too well, but this was on a mid-shift, so obviously they're having fun. There's snow coating the sign outside the Weather Service office, and they made a little smiley face on it. So it's that really wet, slushy type of snow that fell, and since it was 36, 37 degrees, it melted pretty quick. But they did other parts of their forecast area, and maybe, Jay, you remember that. They got up to 2 inches really quick, and some of the social media sites around the area that the Weather Service was tracking had mentioned that people had a hard time seeing because when it changed over to snow, the visibility dropped really quick, and so they got a little worried about this kind of thing. So even though it was kind of in terms of snow accumulation, it wasn't that big of a deal to viewers who are driving or to people that are trying to travel through this stuff. They hit a pocket of that heavy snow. The conditions rapidly change and their visibility drops. So it's still, for travel, this kind of thing I think is gold. It's gold for winter weather, transition events, rain to snow, for travel considerations. Let's move to actually fairly recently, December 19th in the Texas Panhandle. They had you may have remembered they had a pretty good blizzard there. And this event also started out with rain and eventually transitioned into all snow. So Texas Panhandle, at least the northwest part, it's already heavy snow, quarter-mile visibility, and a little bit breezy out there, if you like breezy and snow. Amarillo, 39, rain, so it's still rain, and then it's actually just a few miles south, it's in the 50s. So somewhere in there, it's transitioning into rain, snow. But where and when and what roads might be impacted by that? So here's reflectivity, and it kind of looks like a mess. There's, without dual polarization, I don't know where you'd say melting is occurring. Where is it rain? Where is it snow? It'd essentially be impossible. But to get your bearings, here's Interstate 40, major travel artery, east-west. They're expecting major problems there, but we'll try and figure out where the snow was at the time. So here's correlation coefficient. So again, remember, magenta, it's either all rain or all snow. Where it's yellow, it's kind of a mixture, right? But this is hard to interpret. Even for someone who's looked at this stuff for years, it's hard for me to interpret. kind of following a band around the radar. This is a clear-cut melting layer out here, but here it's kind of all over the place. It's probably melting, so you would first guess, you'd say inside the yellow is all rain. Outside that is all snow. We'll need differential reflectivity to help. Now these are from GR Analyst, and so it's the raw level 2 data. You'll notice it's quite a bit noisier. Why is it noisier? Well, if you're getting the level 2 feed, this is actually super resolution. It's half-degree azimuth data, so it's a lot noisier than what I was showing just a minute ago that the Weather Service uses. So something to keep in mind if you use this. If you get level 3 products, those will be smoothed out quite a bit. But even to me, this is a really noisy graphic to look at. But
the vendors can improve by
yeah.
doing the same smoothing.
Yeah, they could do similar smoothing. I just turned it off just to show just how raw the actual level 2 feed is, how messy it can be. But we start to see patterns, though. Values are higher and noisy in the areas that we thought would show melting, so melting's going on there. In this area, again, where correlation coefficient decreases, transition zone, higher values here. So inside the ring, though, it's kind of interesting. You notice the values are pretty low. So that's where it's tricky. Because those same values we looked at Wichita would have indicated snow. In this particular case, they're indicating really small raindrops, almost like drizzle. I'll show you why that is just a second. For that, we need to look aloft to be able to see a little bit better close to the radar where melting is actually occurring. That's what we got here. So reflectivity. If you remember signature called a bright band, I mean, I don't know where you're going to find it on reflectivity here. With correlation coefficient, pretty easy, right? It's a ring. So inside the ring, all rain. Where the ring occurs, where it's transition zone, anything outside the ring is all snow. So just by looking aloft, cutting that slice, cutting through the atmosphere a little bit higher, within, say, a 2 or 3 county radius of the radar, we can pinpoint at exactly what height, using inside of the ring, what height the melting is actually occurring, and you're getting a full transition over to rain. In this particular case, it's around 2,000 feet. Differential reflectivity shows something similar. We already proved to ourselves that it's all rain in here, so even though the values of differential reflectivity are kind of in that 0.5 or lower range, normally associated with snow in winter weather, we proved to ourselves, at least I hope that we did, that it is all rain in there. They're just really small drops. So going a little bit further in time, so this was about an hour earlier. Let's move an hour later. What has happened to our ring? Definitely shrunk. In which direction did it shrink from? Yeah, isn't that pretty cool? So on the north, it's not a perfect ring anymore. So the cold air coming from the north has lowered the freezing level locally north of the radar. South of the radar, it's still roughly the same thing. So what we're looking at is a sloped frontal zone. Much deeper cold air to the north, freezing, or the melting getting much closer to the ground. Just in an hour's time, you're able to track that. So it's getting closer and closer to the ground in the Amarillo area, and in particular, this major travel corridor, Interstate 40. And that's what reflectivity looked like. So in that case, reflectivity is kind of showing the bright band. You're getting 50 dBz returns there, telling you that's definitely a rain-snow mix. 1 hour after that, it's still 36 in Amarillo with rain. All these sites kind of have gone down. They're getting whited out by 40-mile-per-hour winds and heavy snow. But in the Amarillo area, still reporting rain technically. What's the radar saying though? So here's the lowest elevation angle. So right here is pretty much just right off the ground, a few hundred feet off the ground in Potter County. Higher reflectivity to the east-northeast. That kind of looks like melting, right? And indeed, some of it is, but not all of it. Everything north and west of the radar. It's either all rain or all snow. And of course, knowing what we know as meteorologists, we wouldn't necessarily even have to look aloft to know that that's all snow, because we don't see any melting going anywhere with range. So at this particular time, in Amarillo and along Interstate 40, it's transitioned to all snow. There's still a little bit of melting going on east of the radar. So any questions so far about what we're seeing? This is pretty fascinating stuff for snow detection, rain snow line detection. And that's the thing. I mean, I'm showing you snapshots an hour apart. You're getting this transition zone as it moves across the area every 5 minutes. So you can provide updates. Hey, it's transitioning to snow in this area along that interstate with a fairly high degree of confidence at what you're seeing. There's differential reflectivity, kind of showing what we saw in the Wichita case. Once it gets down to around 0.2, just barely positive, it's all snow. And then
what really good as well. I was telling Don before about with the ASOS out there, when you get these situations, especially with wind, it's very hard to even just determine from the ASOS what the heck is going on, and this is a good way to kind of sift your way through where the rain snow line is and what's really going on.
Mm-hmm. Yeah, it's all this stuff is all about improving your confidence in what you're seeing. That's what we've trained the Weather Service forecasters, and we're hoping that trickles down to, you know, you guys increasing your confidence in what you're telling your viewers. Yeah. Oh, that's right. I'm sorry. So the question was, with ASOS, the automated surface observations being the way they are, particularly in blizzard conditions, it was a comment that radar will increase confidence that, you know, ASOS may not know what you're seeing, but the radar will definitely be able to verify the transition to snow. So this was pretty neat. You know, this ended up being, that is a car buried in eastern New Mexico under 4 feet of snow, and the people were in there for 36 hours. They didn't panic. I was very impressed. So their cell phone was barely working. They called a friend who then called 911 for them or whatever, and then they brought out the avalanche poles, hit the hood of the car, dug them out, broke the window, and got them out of there. But, I mean, so travel concerns, yeah, just figuring out where the rain to snow transition is, giving road crews a heads up on, yeah, it's changing over here or it's still rain here type of thing. And especially for visibility, we saw that in the Wichita case. Yeah, it wasn't a lot of snow, but the visibility drastically changed when it went from rain to snow, making travel conditions a little bit more difficult. How about one more, well, I've got a lot of winter storms, but this one was the start of the Groundhog's Day blizzard that I'm sure all of you were familiar with just in 2011, almost a year ago now. The expectations, so the Weather Service and local media were expecting it to start as sleet, and at times really heavy sleet, changing over to snow. But the timing and the location of where or when that transition would occur was pretty uncertain. And as you probably know, there are huge accumulation differences and road conditions and visibility conditions between sleet and snow. With snow, obviously, it accumulates faster, visibility is a lot lower, roads can get a lot worse when it changes over to snow. So figuring out when that happens would be a big bonus. So here's reflectivity. Again, this is winter storm. We've got there are a few pockets of 60 dBz returns in there. The rest of it is kind of, you know, 40 to 50 dBz all around the outside of it. And then it's a little smoother out there. So, you know, using Meteorology 101, Radar Meteorology 101, before dual polarization, most of us would probably say, that looks like a bright band. That's probably all a transition zone. Out here, the reflectivity is smoother, it's lower, that's probably all snow. So what's in here? What do you guys think? Is it possible to have 60 dBz returns with raindrops that are drizzle size? Basically, that would have to be drizzle at 60 dBz. Is that possible? Drizzle rarely gets above 25 dBz. So there's only one other thing it could be. Check your dry snow chart. And some of these events kind of break those charts because I don't even know, do they even say reflectivity can get much higher than, yeah, it says reflectivity rarely gets above 35. But you'll see this. You'll see this in nor'easters. You'll see this in lake effect snows. What was going on in that band was heavily rhymed snow pellets or grapple that was occurring in there. I mean, ridiculously heavy, 3 inches per hour of this stuff. So you can see that in nor'easters. You can see it in lake effect snow. There was lightning strikes in that area. So there was thunder grapple, thunder snow, whatever you want to call it. It was heavy, it was white, and it really hindered travel. And I don't know how you'd be able to tell the difference in reflectivity. It's outlined perfectly in differential reflectivity. So south of this kind of this shape I drew, it's a melting layer. So underneath that area, it's still sleet. In that band, I-40 just happens to go right through that band.
Sorry, why did you make the drizzle comparison? Or a question about it?
Okay, so for differential reflectivity, there's only a few things that could be 0 dB values, which is what these are, right around 0. Hail, which it's winter, there's not going to be hail. Drizzle or snow. So we can rule out hail, look at drizzle or snow. Drizzle doesn't make sense at 60 dBz. Yep. Let's look at correlation coefficient just to help us. So again, this says it's either all rain or all snow in there. There's nothing else it could possibly be. Outside the shape, it's a transition zone. But everywhere, you can see where the cold air from the northwest came in. Everywhere northwest of the radar was indeed all snow. So this entire batch, everything, all snow.
What about the grapple phase that's on here? Would that match your outlined area?
Yeah, it should. Yeah, look at the values of grapple. That goes up to 50, 55 dBz, is that right?
Yeah. Yeah, that would be best.
So near 0 dB, correlation coefficient all the way up there, then 50 dBz. That matches grapple really well, right, Greg?
That would be also for sleet, would go with the grapple, is that right?
Sleet's a little trickier. Actually, with this particular case was one of the few times in all the radar data I've looked at, I thought I was seeing sleet on the radar. Problem is sleet refreezes so close to the ground, radar rarely sees it. That's part of the problem. Sleet would look like that should you ever be able to detect it, but I don't anticipate many events where you'll be able to see sleet because it refreezes so close to the ground. I mean, you might see it right around the radar, but then you've got clutter to deal with, and it's just really tough. So that's why the meteorologist, the human forecaster, has such an integral role when interpreting these products. So since we know melting is occurring out here below the beam, we don't have a clue what's going on. Well, an algorithm wouldn't have a clue, but as humans who did our homework, knowing how cold that layer is, we have a pretty good feel if it's going to refreeze or if it's going to go as freezing rain or whatever. So again, humans, there's always going to be a role for us humans in figuring out what's going on below the radar beam. Radars can't give us that.
That looks like you have 3 little spikes.
Where?
Southeast, northwest, and northeast.
Oh, yeah, you got it. There are, believe it or not, in Norman, there are some blockages. One's a water tower. 2 are water towers. One's the other radar, right, Don? This one?
Oh, yeah, that's right.
That's the other radar, water tower.
They put the other radar on the same azimuth as the water tower.
That's right.
That's both.
Yeah.
To the northeast, that's a water tower to the southeast, and to the northwest is the Embassy Suites Hotel.
Yep.
Great place to stay.
Yeah, if you want to get radiated.
Again, it's a false radar.
Yeah. Very low doses. So this type of thing.
Right. And
Oh, yeah.
in those areas where we have beam blockages, if you go back to that last one, you'll see it also messes up the dual
Yeah.
cell for everything except KDP.
Yep. So travel. In that band there that's set up and kind of stuck over the same area, they got up to 18 inches of snow, which Oklahoma, that's the end of the world snow. It pinpointed the earlier changeover and where it actually occurred, and would have provided a little bit of lead time on where that heavy snow band's set up, east of the metro. So any questions about what we just, these last few events that we looked at for winter weather? You starting to get a feel for the things to look for in the process for how to determine whether it's rain, snow, and where that is? So I'm showing more. I'll show more events on that. I've got a Cleveland event coming up here pretty soon. Wanted to mix it up just a little bit. Let's get away from winter weather and rain, snow changeovers. Let's go to July in the Phoenix area. This is kind of early in the monsoon season. They're expecting dust storms, severe winds, and then storms firing along those gust fronts. So for something completely different, I put the motion of these things together. So this one's moving out of the southeast. That one's out of the northwest. And then there's, junk, whatever that junk is, and hopefully dual pole will help, as I'll show. Junk all along and behind that boundary that are about to collide over Phoenix. So what does it look like? So correlation coefficient. Anywhere it's magenta, all rain or all snow. Where it's kind of a yellow, it could be a rain-hail mix now because we're talking warm season, not thinking snow this close to the radar. But tale of two boundaries. Look how different behind this boundary is. It's a much darker blue, which means much more randomly oriented things going on. I mean, that's a tornado debris sometimes will look like this. This particular boundary, a little bit higher values. So I wonder what's going on there. Differential reflectivity. This boundary, maxed out positive. What do you think that could be? This one? It's not precip yet, though. It's not precipitation yet. There's no precipitation associated with that yet. We're really close to the ground. Don, the expert over there, how do insects fly? They're kind of grasshoppers and things. They're horizontal, right? Locusts, yes, could be a plague of locusts. Either way, it's insects or birds. When you get the really strong positive values, you got insects or birds. And we've seen this. It doesn't matter what part of the country you're in, on these gust fronts that are moving, and I'm not sure why. Maybe they like the change in temperature, but insects and birds, well, if the insects are flying, birds are flying because they want to eat the insects.
Yeah, I think the insects, they're not steering their own course. The wind moves them along.
Yeah.
And the birds go where the insects
Yep.
are because the birds like to eat them.
Yep. And so, yeah, any part of the country for most gust fronts will look something like this, with really strong reflectivity returns and correlation coefficient that says it's not precipitation, it's biological. But this mass coming from the southeast, completely different. In fact, these are ridiculously negative values, minus 0.4, about as low as you'll ever see on the radar. Turns out that this was the haboob. So it gives you a different flavor of what is actually making up the gust fronts. And for that one, it was dust. But research, I mean, I haven't heard anyone that has explained what the heck that is, why it's so strongly negative. There wasn't any reports of lightning or thunder inside the dust, which can sometimes happen, which might cause a negative ZDR. But it's probably likely. It's likely there's lightning down there, yeah.
You can electrify things and then orient particles.
Yeah, even without lightning discharge, right? That's what you're saying, yeah.
Some people postulated, and Paul was a part of talking about all of this, is that some people postulated it was chaff. They do have chaff releases out there that very, maybe some chaff got picked up and could get oriented in a vertical background. It's a head scratcher.
In any case, it's just a neat example of how dual polarization can loosely identify, well, at a minimum, tell you that there's something different about these two approaching gust fronts.
Could it just be the nature of the dust from the haboob?
How can you have dust with vertical orientation?
Yeah. Yeah.
Particles are pretty darn fine.
I did a quick Wikipedia search. It's amazing what you can find on there. They had a zoomed-in image of actual dust particles from a Moroccan or Sahara haboob. And based on that and everything I read about dust, you'd expect ZDR to be 0 because it's randomly oriented. It's all, there's no preferential direction or shape to dust. It's dust. It's kind of like hail, where it'll be roughly 0. In this case, it definitely was not 0. Very interesting. Yeah. Aliens. So that one was interesting. Any questions on Phoenix here? This is a really neat event because once those gust fronts collided, then convection kind of zipped all along it, and so you're able to track where the new storms were forming all along that collision.
Did you see the video of this helicopter?
It's crazy. Yeah.
The reflectivity, the velocity.
Oh, I didn't show it, but I believe it was probably in the 40 knot range. I mean, it wasn't gonna knock you over, but it's still, you wouldn't want to be outside in that, particularly with the dust. All right. We have Washington State, the new Langley Hill radar, which, yep, in September. Unfortunately, you guys had a pretty good, for you, a drought in December, Or not till the end, right? You finally got something?
We're still dry.
You're still dry. See, before coming here, I'm like, the one thing I wanted was a really good winter storm in the Pacific Northwest, and it just never happened. So I was going to at least show something from up there, just to show that the same concepts that I've been showing other parts of the country still apply in the Northwest. So in September, obviously a pretty good Pacific storm with towards the surface, more southerly flow, really strong too, actually. And then once you go further aloft, it's more of a southwest direction. And we're talking 80, 90 knots, not too far off the ground there with this storm. So you see there's echo just about everywhere covering the screen. So let's take a look at what dual polarization might tell us about the echo. So that's interesting. Just offshore in here, correlation coefficient is in the blue range, which is around 0.5. So could that possibly be precipitation? What do you guys think? Is there any precipitation that falls into that blue range?
What's the second? Drizzle, snow drops, maybe some.
Oh, I'm sorry. This is correlation coefficient. We'll get to differential reflectivity next. Yeah, for what I'm doing here is it precipitation or non-precipitation? That's all. Since it's a warm season event, not too concerned about snow yet at this level. So it's either precip or non-precip. So in the blue area, is it precipitation? Can't be. You never see precipitation get this low in correlation coefficient. But everywhere outside that, where it's magenta, it's either all rain or all snow. And since we're talking September and you're already expecting snow levels probably as high as 9,000 feet, that's all rain. So that kind of takes the mystery out of if it's magenta, there's no mystery. It's all rain. So differential reflectivity, strongly negative in that offshore area. Everywhere else, it's around zero. So yeah, it's roughly drizzle. You're getting drizzle. Well, although this fascinates me. So okay, so it is a little bit higher in this band, differential reflectivity, which would indicate the drops are a little bit larger, higher reflectivity values. But what the heck is offshore down here that's not precipitation, but it's yet getting really strong returns?
S-band radars don't see
Yeah.
warm clouds very well.
Yeah.
Particles are so small.
And negative differential reflectivity, again, it just doesn't happen. It happened in that dust storm. Something really weird would have to happen to get negative differential reflectivity.
You know the answer, or you just throwing it out there?
Just tossing it out there. We think we know the answer, right, Don? You're getting a lot better. Yeah, sea spray. Or the waves themselves, the tops of the waves themselves as they break offshore. So, yeah. So one of the applications of this is, at a minimum, these areas here won't get counted for precipitation amounts because it's clearly not precipitation based on that. But from another aspect, you're seeing, yeah, where the waves are breaking, where there's sea spray going on. There's sea clutter out there.
So why there, not elsewhere?
Yeah, that's a really good question. That I don't know the answer to. It could just be the way the waves were breaking and the orientation to the radar. Yeah.
What was the direction of the fetch out there?
South, right? Strong south.
Activity is so low, though, that it doesn't look like it should be a solid ground clutter kind of.
How high is the beam off the surface of that?
Well, if it gets ducted, it could be hitting the surface of the water.
Go back to it again.
Yeah. And this also fascinates me. It's almost like you're drawing a line along the coast. There's no sea clutter here, but there is along here. It's weird. Just interesting things that research would be able to provide.
Paul, somebody was explaining it. I can't remember now the explanation about in sea spray how you could get vertically oriented particles.
Yeah, I hadn't heard that, but that's interesting.
Can't remember who was offering that, but apparently it's possible. Not like that's exactly what it is, but
Mhm.
it's possible to get vertically oriented sea spray particles.
And they were seeing similar stuff off the Carolina coast with Morehead City radar also, where they'd see this line of higher reflectivity, really low correlation coefficient, and negative ZDR. So it's not restricted to just the Pacific Northwest. Apparently, whatever it is, when the beam impacts the surface of the ocean where the waves are breaking, and there's a lot of sea spray, you'll get signatures like this. So kind of fascinating. Other than that, though, outside of that, not much else going on. It's rain. Where there's heavier rainfall, the differential reflectivity was higher, just a little bit higher, indicating a little bit larger raindrops. The rest is kind of drizzle.
Something I would point out, like I mentioned, for different environments, those ZDRs don't get a whole lot higher like you would expect in a continental storm. This is a very moist environment, very high humidity, emphasis on larger numbers of smaller drops.
Mm-hmm. Yeah, maritime drop size distribution. A lot of warm cloud stuff. So let's look aloft. Maybe we can, I mean, in the winter, it's much better to look aloft because then you can really pinpoint where that rain-snow line is transitioning, especially for the mountain ranges out there. Reflectivity would be pretty tough to find where that rain-snow line is. But with correlation coefficient, really nice ring. It's actually constant height too, so all you'd have to do is find out what height this is, what height this ring is around the radar, and that's where it's all rain at that point. In this case, it was well over 9,000 feet.
There was a case just I think last week.
Mm-hmm.
It was a weak storm, but the Weather Service was talking about this in their discussion off this radar, showing the melting level and helping them with the freezing level.
Yeah, and that's one of the things that if you're interested in taking the training, and it's the same training that the Weather Service has gone through, it's the module I put together. I always tell them, get a feel for the environmental conditions, and then look aloft. Because if you're lucky enough to find a nice ring like that, you've got your answer right there. Where the melting level is, at what height it's transitioning to rain snow. It gets a little trickier in more complex events like that Wichita one I saw, where there was no nice ring. Or Amarillo, where that ring was kind of funny shaped because of the sloped frontal surface. So for non-weather echo, which is we saw the sea spray, we saw the dust, but the potential is there, and I think Don showed this. The potential to really clean up your radar displays, to just, if you wanted to, and I'm sure vendors have already done this or are working on it, to clean up those displays so that you're not even showing the insects, the birds, the dust, chaff, whatever might be out there. Using correlation coefficient and seeing where it drops off, you can really clean up your radar displays. And then how does that help you? For precipitation totals, getting amounts from clear air returns will be a thing of the past with dual polarization.
Make sure you mention to the vendors you need two products, though. You need one that's still got that clear air reflectivity and velocity data, because you can use it, and then another one that's just the precipitation.
Mm-hmm. Okay, let's get to some more. Go back to winter. Figured I'd show an Indiana, Illinois event. Anyone from around that part of the country? Not, okay. But it's very similar to the other events we looked at. You're expecting rain changing to snow. It's near the end of the precipitation as the cold air is deepening. And that's particularly in northern Indiana. Very similar to Wichita. Temperatures were mostly in the 40s, so pretty tough to get snow there, but you'll notice that in this area, mid-30s, then you're in the range of where it could be snow at the surface. And indeed, at least this site in Indiana, snow with rain kind of west of that. So the radar is going to be interesting. Maybe it'll be able to show what the differences are. So at roughly the same time, here's what reflectivity looked like. And it's decreasing. This is correlation coefficient, so where it's yellow. Again, that's where the transition zone is. So almost everywhere you look, and we're a little ways from the radar. We're probably 3,000 or 4,000 feet off the ground. It's still melting at this particular time, at least at that height. Let's go a little bit late. Differential reflectivity, all strongly positive, indicating it's probably a lot of liquid in there. Further at range, out here, it's at snow, but then you're so far off the ground, what happens at the surface, probably you can't even really tell. Going an hour later, still it's 34 in heavy rain here, and then 34 in snow, moderate snow there. The unfortunate thing with this event is that we didn't have a dual pole right here. The radar's all the way up there. So figuring out what that is a little trickier. Reflectivity is still in the 30 dBz range. Now correlation coefficient has changed everywhere to 0.99 just in an hour's time. So without even looking at differential reflectivity, is that all rain or all snow? Just use your meteorological sense. Yeah, I mean, it would have to be, because out here we're at like 7,000 feet. It's not going to be liquid out there since it's high everywhere. We're talking all snow there. And eventually it did, so I didn't even need to show differential reflectivity in this case. If we looked at it, you would have seen that it was all decreased into the snow range. And they were getting some snow at the surface, but the thing is, they were still getting surface reports of rain in certain parts of it. So again, far off the ground in this particular case, it's a lot trickier to get a good feel for what the precipitation type will be at the ground. Questions? All right, here's yours, Betsy. Just actually about a week and a half ago, it was expecting rain and snow mix, changing over to snow later in the event. And we're looking at the Cleveland radar here. So here's your, yes, you just gotten it, right? Just before Christmas. So it's 36 in rain in Cleveland, 33 in rain, 36 in rain. And then there's snow down here. So again, this will be interesting to see what the radar says. So here's your reflectivity. In here, we like seeing this here because it's so close to the radar. We should have a pretty good feel for whether it's rain or snow in that area. Out here, it's more like 1,000 feet off the ground. Might be a little trickier. In Canton, yep. So there's correlation coefficient. So what do you guys think? Is there snow in there? Yeah, right here, right? Nope. So melting all along here.
I didn't get it. That's about 4.5 inches of snow.
Yeah. But
I know, right?
trust your instincts. Where it's yellow, you know there's melting. So since we're already 1,000 feet off the ground out here, it's probably going to go to all rain here. But in here, that could be an issue. So we need differential reflectivity to help us. If it's around 0, we know it's going to be snow in that band. Oh, that's lovely. Even though it's a noisy, noisy product. Notice how pretty clear cut that band on the lakeshore Betsy knew about, and then this band. It's all snow. Everywhere else, it's going to be rain at the surface. Now, with reflectivity, would you ever been able to tell? Out here, probably. That kind of looks like a normal melting layer. But here? So right here in this northern Medina County. Medina. Tell I'm not an Ohio native.
Where I live.
Oh, nice. Was your house under this? Okay. 35 dBz, all snow. Lovely event. 6 inches. Not much everywhere else, right? So, yeah, again, you're getting a heads up on this band and on this band that that's snow. The rest is going to be rain. Fascinating stuff. Let's see, I go a little bit aloft because there's a lot of clutter in the Cleveland area. That's what all these blanked out spots are. So I want to look aloft just to see, does it look a little bit different? Does it look a little bit easier to see? I'm at the next tilt up. And it's very similar. So above that band, it's still all snow. You can see where there's melting occurring very close to the radar, but outside that, it's all snow. And same deal. Higher differential reflectivity, melting, more liquid. Where it's around 0, all snow. I'll go over this again.
We even had a few rumbles of thunder reported by viewers north of the radar there, right on the lakeshore.
That's impossible. Can't throw it in there.
So I don't know, I mean, Betsy, what do you think? Could you increase your confidence of where rain and snow is occurring in the Cleveland metro area?
Yes, and I would also like to move it about 25 miles east into the snow belt where it was supposed to fall.
Oh, yeah, gotcha. So again, forecasters, both broadcast meteorologists, weather service, increasing confidence where this stuff is going to be transitioning. How about some more warm season stuff? It's been cold for a while. Let's go to warm season. Go to the Carolina coast with Hurricane Irene. So you're going to see hurricane dual pole data. As Irene was approaching, they were expecting outer band supercells. Hail is out of the question in this particular event. So So why would I say that? When you look at these images, any decrease in correlation coefficient is not likely to be due to hail because hail shouldn't exist on these things. Any decrease in differential reflectivity should also not be indicative of hail, just be indicative of smaller raindrops, just because we're kind of ruling out the presence of hail with a tropical storm. So here, I'll toggle between these two. There's velocity. You have a tornadic vortex signature with the really strong outbounds right next to the really strong inbounds. Notice it's kind of in this, the outer band is moving like this. It's kind of an interesting location for that to be. There's also some pretty good shear with that storm there. So they had a tornado warning out for this because you see that you better issue one for the benefit of everybody. But what about dual polarization? Notice right where that circulation signature was, there's a pretty steep drop off in correlation coefficient down to about 0.9, which if you're looking at your charts at a rain-hail mix, that falls into the range of rain-hail, rain mixed with hail. But it's on the lower end. It's 40 dBz roughly. Lower correlation coefficient. Does it make sense that there would be hail coincident with a tornado signature? Usually hail kind of falls on the fringes of the updraft, and plus it's a tropical environment. We're not expecting hail. So not much else can explain what that signature might be. Differential reflectivity. It's not showing a whole lot. Again, near zero would be hail or very small drizzle drops. Where it's increased, the drops are getting just a little bit bigger. Everything there is fairly typical of a tropical system with tropical sized drops.
Not much evidence of debris.
Yeah, not much evidence of debris, but I submit that we are seeing debris here. And research and all the examples of debris that I've looked at has shown that in storms that are completely covered in rain, you're getting tropical rain right on top of that tornado, all around the tornado. When little bits of debris, and in this particular case, it's probably just leaves, pine needles, whatever else is out there, frogs, as it gets lofted and coated in water, your differential reflectivity will still remain somewhat positive because it has a little bit of a water coating on there. Other signatures on that day. Now this is out and kind of right along the Pimlico Sound, where the hurricane's approaching. It's 9 o'clock at night. You're not going to get a spotter out there, so there's no way to verify that really was a tornado. But other smaller supercells did hit something, did hit a town, and did get reported as a tornado. The signatures looked very similar to that one. So in this particular case, they had a tornado warning out for it, but had no way to verify it. In this, with dual polarization, they're able to at least, if they could send a team out there to verify that there is some tree damage, that would be one thing. But there isn't much else that can explain that signature other than tornado debris. And again, it's not big pieces of debris. It's little tiny pieces of either leaves or twigs or something like that.
Did that feature show up in a temporal way on the
Yep. Yeah, and that was the other thing. It didn't just last for one scan. It was fascinating. And probably because of the really strong horizontal flow, whatever those little bits of debris were, you could track it for about 20 minutes as it went across the screen. Even though the circulation had died down, it was still, 70-mile-per-hour winds from the hurricane was keeping that stuff aloft, and you could track it as it moved away. Which was another bit of information that kind of made us think that, yeah, that is debris in there. It wasn't just some spurious feature. So tornado debris, even weak tornadoes. So they didn't even know that was a tornado there. Probably too late to do a damage survey. But it's not going to give you lead time because the tornado is already there doing damage before you see the signature. And it also, in most cases, needs to be pretty close to the radar. But for forecasters, broadcast meteorologists, these types of signatures, and I'll show a couple more, really will increase confidence that what you're seeing is actually a tornado and not just some radar-identified signature. So that weather service forecasters are able to go from radar has detected a storm capable of producing a tornado to confirmed damaging tornado with dual pol. Verification. We just saw that particular event right there from Morehead City. They wouldn't have known that that was a tornado without this type of data, so they're able to at least get a little bit better verification. And then one other thing that really should help, say you've got a really, like a Greensburg type tornado or a Joplin type tornado, which in the case of Joplin, they were getting reports pretty quick that massive damage was occurring. But in areas where maybe communication is knocked out, it's maybe an isolated place where reports can't get out, Weather Service and broadcast meteorology folks can see a debris signature and kind of know where the heaviest damage was occurring along the track. In the first 5-10 minutes after a tornado passes, that's when you got to get those EMTs and the fire department keyed into where to go, where the heaviest damage is. So these types of things, though it won't be a bigger lead time, you'll be able to get those first responders in place quicker than you would before dual polarization. So this is now we're talking tornadoes, a very recent event just before Christmas, near CNN and the Weather Channel, near your neck of the woods in northwest Georgia. Did have a tornado watch, but it was a quasi-linear system event. So tornadoes were at least possible, minimal hail threat. So we're looking at a line of storms. I mean, there's storms everywhere around the radar near Atlanta. So as forecasters, we kind of key in on little hooks in the data, hooks in the velocity products. You're not going to see it in reflectivity because it's just raining everywhere, heavy raining everywhere. But we'll key in on some of these features in a little bit. So we want to look for debris. Always start with reflectivity, always start with velocity. And then go to correlation coefficient. Again, we're right near the ground. I'm not sure. Is that terrain, guys? Atlanta experts? Is that terrain, or is there buildings out there near the Peachtree City radar? Is it terrain? Terrain and trees? Trees. So getting that close to the ground, this product is always going to be noisy. Even when they smooth it, it gets noisy. So it'll be tricky to identify if there's any debris. But at this particular time, that just looks like clutter. If you were to loop this, the clutter stays in the same spots, which kind of helps you understand that, yeah, that's probably not debris at that time. So nothing, it appears at this time, nothing's really going on. Differential reflectivity, it's all over the place. We're not too concerned about the presence of hail. So wherever the differential reflectivity is lower, it's just smaller drops. Where it gets higher, much bigger drops. That's kind of all that's really showing, since it's all rain. Going a little bit later in time, that right there, we're right by the radar. It's a nice rotational signature, plenty of shear. It's roughly 70 or 80 knots of shear. And then there's another one kind of right there with a little velocity hook. Interesting. Where's it located? Again, there's no way you'd be able to pick that on a reflectivity, what's going on there. This thing's embedded there, that's embedded in that batch of precip. So who knows if that's a tornado? I'm almost positive they had a tornado warning out for this. I should have checked ahead of time, but almost positive they had one out for those two signatures right there. Let's look aloft, because again, we're so close to the radar. Even at the 1.5 degree tilt, we're still not even 1,000 feet off the ground. And that signature looks really good at this height too, and so does the other one. Move forward in time. Also like using, when you're this close to the radar, using a little bit higher tilt to get out of the clutter. So now this one looks really good. This one, still something there, pretty good rotational signature. Weak, don't get me wrong, they are weak. They're not going to, embedded in heavy, heavy rain. There's no way anybody's going to see this unless it's right on top of them, they hear it coming. Now there's something interesting. There's a little blotch right there. Right where that tornado was.
Is that correlation coefficient?
That's correlation coefficient, yeah. With this type of event, I don't even bother with differential reflectivity because, I mean, it's noisy. The clincher for debris is correlation coefficient. You have to have something that caused it, i.e. rotation, and then you have to have a lower, slightly reduced correlation coefficient. So right here, there's something going on there. Remember, it wasn't there before, so this is an area where clutter is not known to occur. Right there. How about the northern one? Northern one was right here. Yeah, so at least at this height, which we're about 1,000 feet off the ground, that one doesn't have debris, but this one almost definitely does. We could look at multiple tilts to see, you know, how high does the debris extend? Is there any continuity? And sure enough, this one right here actually goes up to 5,000 feet. You could keep looking at higher tilts, track it, it's 5,000 feet high.
Oh, you have another signature right around the radar, northwest, southeast.
This? That is zero, kind of the zero isodop. Clutter filter is removing that. So yeah, that's another reason.
And it's then biasing the other, the dual hole variables, and so you're getting poor estimates.
Yep. So we have debris here, and we go. Let's see, how much later in time do we go? Yeah, the next scan. Next scan, that signature is still there in velocity, but on velocity here, there's a tiniest bit of shear left over there from the original circulation. There's your reflectivity again. It's heavy rain everywhere. You're not going to see these things. You're probably not even going to see the debris necessarily. But now you can see the elevated debris. Even though there's probably not a tornado at this time, given the velocity, there's still lofted debris, little bits of trees right there. But notice that one, right on top of it, right? Debris. That is not a known area of clutter, so with that one there's debris. And right now we're roughly 2,000 feet off the ground.
There is a tendency with some of these to issue tornado warnings that are for broad areas. One warning to cover large areas. I am not a fan of that. We ought to issue warnings for where we think the threat is to prevent what's already a bad false alarm
Yep.
ratio.
What's the distance from the radar for those two?
Like 10 miles. It's really close. Even at the 1.5 degree tilt, we're just over 1,000 feet off the ground. Really close.
Paul, could you summarize the discussion going on?
Don, what did you say again? It was.
I said there's a tendency sometimes to issue one tornado warning to cover a large area for events like this, where we have small, sometimes non-supercellular signatures that are evolving rapidly.
Right, so there's a tendency to have larger tornado warnings to cover an entire area like this, but as we're seeing in this particular event, that they're actually really small, kind of short-lived circulations that are the reason for this. And we're about 10 miles from the radar, roughly 1,000, 1,500 feet off the ground. From the 1.5 degree tilt, the half degree tilt's only a few hundred feet off the ground.
Have the operational Mets changed how they issue the watches and warnings, or is that an ongoing discussion?
It'll be ongoing. Yeah, as far as I know, I mean, they didn't even see these in real time. This was all kind of after the fact, after they were looking for places to do storm surveys. They saw one down here and sent it to, there's a list server that, you know, people will look at the radar images and kind of give feedback.
Isn't that where you would apply your significant, weather, what is it, significant weather alert?
Yeah, a statement, right. So had they seen this in real time, and maybe they did, but I mean, everyone's still learning. It's a massive learning curve. What they could have done is issued a severe weather statement for these, saying, yeah, they confirmed debris in the air, you know, located here. As it was, the main uses, I'll go a little bit further and show that you can still track these things. Yeah, and it's kind of embedded in clutter, but the trick here is time continuity. You can loop this and see that that little pocket of debris was moving along with the mean flow there. Even though there wasn't a tornado on the ground, there's still some elevated tree debris up there.
There were 0 and 1 tornadoes confirmed, I think, in that area this day.
Yep.
Interestingly, that though farther to the north up there, there was a little gap in line segments, and there was an EF2 and an EF3 tornado.
Yeah, so Greg was saying that north of the radar, there was EF2 and EF3 tornadoes that much longer lived. I looked at the data for those, and they were just a little too far from the radar to get debris. I never saw any debris. It was only these little weak ones really close to the radar did I ever see any debris. And so from a usability standpoint, I mean, how useful is that type of signature? The signatures are so short-lived. So in this particular case, it was used mainly to know where to do a storm survey. Sure enough, both of those were associated with really short-lived 1 mile path length, mainly tree damage. EF0, EF1 tornadoes. So there is even a utility for post-storm analysis. You kind of know or have a better understanding of where to send teams out to look for damage. Obviously, for weaker tornadoes, it is very beneficial to have them nearer the radar so you can actually see the debris from them.
Can you comment briefly on why Don said that the clutter filter being on creates a bias in the correlation coefficient?
When clutter filter is applied and it removes the reflectivity signal, all the dual polarization products are loosely based on the return signal. So once it gets low enough here, the estimates for the dual polarization products just get really bad. You want, the stronger the signal, the more accurate your dual polarization products will look and behave. Because it removes so much signal in this area, you can't trust the dual pole products at all in there.
Just in that area or through the whole product?
Nope, just where the power gets reduced, and you can see in reflectivity where it's being reduced.
Just an aside here, we're seeing the low correlation for debris with the tornadoes. What about for microbursts? Have we looked at any microbursts that are kicking up leaves and stuff like that? Has there been any?
Yeah, and I did, and so Greg asked if the microbursts have ever been looked at. Norman had a ridiculous microburst. It was EF1 damage, roughly, Don. High-end EF1 damage, very close to the radar, so the radar scanning a couple hundred feet off the ground. Problem is clutter. Very hard to tell the difference between clutter and debris. The other problem is with microbursts, because the debris in these two cases, most likely, so the tornado churned it up and then it got ingested in the updraft. The updraft takes it and runs with it, and you can see it. Microbursts, it's almost all downdraft, so all the debris is confined pretty close to the ground. So I have yet to see a straight line wind event or microburst that has kicked up debris. I'm not saying it's not, it's possible, but it's in my opinion pretty unlikely to see any debris from those. I mean, that was a prime event where that Norman microburst, there was zero visibility and dust and leaves and debris, and I couldn't pick out debris from it on the radar.
We had a later one at slightly longer range, southwest of the radar, later this fall, November, I think. And there was some indication of light debris that I would call it a downburst, not a microburst. It was a broader feature, and probably had some of the particulate matter getting raised to slightly higher heights, so the radar could see.
Yep. I won't spend too much time on this one because this one, not that any radar image is boring, but this one is a little bit more boring than the others. It's just a typical average thunderstorm in eastern North Carolina. There was a watch out for just, the up to 2-inch hail, 70-mile-per-hour winds. No supercells expected, just kind of multi-cells. But so if you want to go to your that handout I gave and go to the rain hail, if you want to follow along with this one, the hail detection. So how do we detect hail with dual pole? Well, as with any, before dual polarization, you obviously look for higher reflectivity. So we'd restrict our focus to kind of these areas where there's higher reflectivity. And we're mainly focusing on this cell. So we'll look at the higher reflectivity and toggle to differential reflectivity. And so again, what values are you looking for hail? What does it say on there? Differential reflectivity. What values does it say on there? Yep. So so the higher values mean the hail's completely coated in water, which means it's almost completely melted, probably won't reach the ground, definitely won't be severe. So though there could be some hail in there. We'll look at correlation coefficient next. Anywhere there's high ZDR, the values above 2, above 3, that stuff is mostly melted hail, probably won't reach the ground. If it does, it's going to be small. But we want to look for these values near 0, the much lower differential reflectivity values, which means all the hail and rain or whatever is in there is mostly spherical, which means that the hail has lasted long enough that it's not this, this ice core raindrop. It's mostly hail. So we're able to detect to pretty good spatial resolution where the actual hail shaft or where the hail is most likely to reach the ground in a storm. And this is for North Carolina. All right, specific differential phase. We hadn't looked at this much because it's the real utility here is in warm season, and it's KDP to me, understanding the details of it, not that important. Easiest thing to think, as values increase, heavy rain. Rain rates increase as KDP increases. So even in here, this whole area has really heavy rain, but I don't know if you can see, there's a distinct minimum in specific differential phase. It's about in the one degree per kilometer range. Coincident with the low ZDR, coincident with the high reflectivity, which means there's not a lot of liquid in there to explain the high reflectivity. It's mostly hail. So again, without much water, that hail's probably going to reach the ground right there.
When would you get into those negative values of differential reflectivity if the hail is just weirdly shaped?
Or really large. I'll show you. We'll get to a much more interesting hail case. So correlation coefficient should decrease where there's hail present, and sure enough it does. It gets around the 0.95 range. On your chart, that's squarely in the middle of where hail should be. So all signs point to hail in that little pocket of that storm as a whole. The rest of the storm, probably you wouldn't need to worry too much about hail reaching the ground. It's mostly rain at that time. So detect pockets at a local level. Get a much better handle on if hail is melted or mostly melted. Size estimation, it's going to be promising, and I'll show why that is next. Going to more of the big bad storms of the plains. 2 events, both from May, both from central Oklahoma. Tornado watch, both particularly dangerous situation tornado watches. You're expecting supercells with giant hail, long track tornadoes. So here's the case right here. Differential reflectivity is actually negative or near 0 in there. And notice where it's located. So reflectivity is saying, yeah, it's high. It's 55 to 60 dBz. But your differential reflectivity is ridiculously low. Very interesting. So what the other piece of the puzzle, correlation coefficient. You guys still have your hail chart open? Gets down to 0.8 or 0.75 correlation coefficient. What range is that in on there? Gigantic hail. The only thing that gets this particular product holds for Rayleigh scattering, which is when the particles that the radar is scanning are roughly small enough or comparable to the wavelength. When you get gigantic hail, this breaks down and the product will decrease rapidly into the greens and blue ranges, which is around 0.8, 0.75. So biologicals or large hail would make sense here. Biological scatters in near 0 differential reflectivity don't make a whole lot of sense, particularly in a supercell where there's precipitation is heavily falling there. The hook echo is right here. So the updraft, the edge of the updraft is right along here. So from a human perspective, the largest hail falls right either in the updraft or just on the fringe of the updraft, right in this area. So incorporating your knowledge of storms, giant hail makes sense here in those areas. They got 4.5-inch hail out of this, crashing through, actually bigger, I think it was 5-inch hail, in this pocket here as it crossed I-35 and went through more. So verifying that it's possible to key in on where those, it's almost life-threatening. If you get hit by one of those, you're not going to have a very good day. So for life-threatening hail situations, dual polarization has really strong promise. You're not going to think that giant hail exists here. Reflectivity looks pretty benign. With dual polarization, you can possibly say that. Does anyone see debris on this particular image? So here's velocity, correlation coefficient, differential reflectivity. So pretty easy to pick a debris ball out there. Reflectivity, would you be able to pick it out? No, not so easily. And on the ground, would you be able to see that tornado? What do you guys think? No way. Look at this. 50 dBz surrounding the entire tornado. You're not going to see that. Radar sees it. You can track it, find where the debris is. Lots of important things that can come out of that. So complete confidence that you're seeing probably an extreme tornado given the rotation and the debris signature there. Here is, we'll zoom in a little bit more on a similar supercell. So we're focused here. Check velocity first. Where there's rotation, let's look for debris. Here's the hook of the supercell, so it's kind of on the tip. That's right where you'd expect the rotation to be. So restricting our focus here, we need to see if there's going to be any debris. You guys think there's debris there? Let me go back. Right here. Debris. Yes, you're looking maybe right there. Yeah. So here's where it gets a little tricky. In really weak signal like that, correlation coefficient can have some problems. So even though that might look like debris, it's actually not. It's just weak signal. The debris would be in this hook part. And at this time, there's not. What I should have told you is that this was the first time that circulation really got going. So the tornado had just started the tornado just formed on the ground. We're 4,000 feet up. It didn't have time to loft debris yet. The next scan, as I don't have it, but the next scan show a massive area of debris associated with this. So there's a lag time. Tornado forms, even though it's on the ground doing damage, there is no debris. It's because we're 4,000 feet off the ground. So you always got to be a little bit careful, you know, putting complete faith in detecting debris, because there is going to be a little bit of a lag time. Let me go to something that's really neat. I think I've got a few minutes. Something we didn't necessarily expect. This is from the same case. So here's the big bad tornado, nice debris ball. Here's the damage track coming headed right for the radar. There's the velocity. I mean, it's actually sampling the tornado. We're seeing the tornado on radar. Then kind of goes this direction. There's still the hook, the rest of the supercell, but the rotation's completely gone. So the tornado picked up, nothing left of the tornado. So there's still, you know, all this precipitation, right, from the supercell. As it moves over the radar, continues on that direction, and then all the way up there. There was no tornado associated with it. The velocity was saying it had lifted. But watch what happens. So this entire blob of reflectivity, I don't know that we would have ever thought that this entire thing is debris. Everything out here is debris. When you start to get again to the more magenta color, that's when precipitation is more likely. So this entire blob of reflectivity, debris. Watch how the debris fans out. That whole thing is debris. On top of the radar, debris. That's still debris.
How'd the radar do?
Tiny bits of debris. That's the key. For something to be lofted for a half hour, even in a severe thunderstorm like that, it's got to be little pieces of paper, like a piece of a yearbook, pieces of insulation, pieces of grass or leaves or twigs, just slowly falls out. You know, that stuff falls slower than a raindrop in most cases, if it's the really light stuff that just kind of trickles to the ground. And numerous reports, including Don and Jim can verify, who lived in Norman at the time, numerous reports of just these pieces of debris from that EF4 tornado were falling 30 minutes after the storm had done it.
It was the second storm to the west that approached northwest Norman. Debris fall from it.
Yeah.
Would chaff behave the same way?
Yes. Very low correlation coefficient, takes forever to fall because it just kind of wafts its way down. So just things we never thought of, that a half hour after a tornado dissipates, we can still see and detect debris and give people a heads up that, yeah, debris is going to be, it's going to be small debris and not pose much of a threat, but it will continue to fall out of a storm. Let's go to one heavy rain event and then I'll wrap it up. So this is the last one I'll show. It's from Pittsburgh in August. The office was expecting heavy rain from somewhat organized storms. They weren't necessarily expecting tropical-like convection. There wasn't a tropical remnants or anything like that. Just it was a moist environment, lots of heavy rain expected. So Pittsburgh, as you know, very hilly city. There's clutter issues all over the place. So looking at the lowest cut can be pretty noisy. But this is what it looked like. So the heaviest reflectivity is kind of along this band here. And that particular band right on top of Pittsburgh, kind of near the downtown area.
That's called the T-bone effect.
Yeah. Nice. So there could be some hail in there, but it's tough to, again, it's either all rain or rain hail. Where it's magenta, it's all rain. Where it's kind of dropping into the 0.995, it would be rain hail mix. But with clutter, it's kind of tough to tell the difference. It sure doesn't look like there's much hail in there. It's probably mostly rain, even though reflectivity is high. Differential reflectivity, if the hail is going to reach the ground, you need to have reduced values. It's on. If you still have your hail chart open, that whole area is 3 to 4 dB of differential reflectivity. So if there's hail, it's completely coated in water, probably won't reach the ground as hail. It's just going to be a lot of heavy rain. KDP, higher values of KDP mean what? Remember? KDP is good for one thing, heavy rain. So when you get to the greens and the oranges, that means really heavy rain. So, and that's really heavy. That's up to 5, which translates into roughly like 8 inches an hour rates. So it's dumping right on top of downtown Pittsburgh. It's dumping in this area too. Problem is, these are actually moving. That one is not. So I'm going backwards, now I'll go forwards again. So in 5 minutes, in 10 minutes roughly, that hasn't even really moved. That rain has really decreased. Go forward again, one more scan. Still hasn't moved. 8 inch per hour rates. Still hasn't moved. Right over downtown Pittsburgh. Yeah, everywhere else, for the most part, it's moved. Still hasn't really moved. And again, this is where KDP is really going to be your friend for heavy rain events. Yeah, there's lots of areas of reflectivity, 50 to 60 dBz, but it really pinpoints where the heaviest rain is falling, and so you can focus your efforts on those areas. So this is roughly a half hour after it started. We're still getting very high rain rates in the 3 to 4 inch per hour. Finally starting to decrease in that area. So I think what verified, if someone can correct me if they knew about this one, I think they actually did get 3 inches in a 30 to 40 minute period. And the water rose, led to a fatality in that area of Pittsburgh because it just rose so fast. But using KDP when you're expecting heavy rain gets you to really pinpoint where instead of looking at a kind of a messy reflectivity picture where different rain rates might occur, KDP tells you, hey, focus on these areas. That's where the heaviest rain is going to be. Any questions on heavy rain? I won't even look at that one. Getting ready to wrap up. But so KDP doesn't care if there's hail in there. It's only measuring effectively how much liquid is in there. In the face of uncertainty, so when you're not sure if there's hail, when you're not sure if it's a tropical-like environment or a larger drop environment, KDP doesn't really care about that. So for heavy rain detection, that's the thing you want to try and focus on. Don put this website up. It's the H should be on the outreach, but that particular course is designed for broadcast meteorologists. So what it is it's an introduction overview, kind of giving you a feel for what to expect as you go through any training, and geared towards you. And then and I'm sure all of you are much more experienced than most people. You'd want to take the full version of the training, which is kind of what I just went through. It's kind of more advanced techniques. It's how to detect hail, how to detect debris, and that's all part of the training. Yep, I'll leave it up for a while. So any questions? I'm kind of curious to hear what you guys think about if you'd ever show this on air, if you'd ever show a dual polarization product on air. Yeah, Paul.
Seems like a lot of the examples were fairly close to Doppler.
Yeah.
Is that a limitation?
Yeah, and that's true of even before dual polarization. That's true. I mean, who knows what happens below the beam? The real advantage here is once you get close to the radar, the lowest 1,000 feet, chances are whatever you see at the radar is not going to change before it hits the ground. So that's why I kind of stuck to close to the radar. At far range from the radar, you can still detect what the radar is seeing, but 4,000 feet, that could and probably will change quite a bit more. So at further range, these types of techniques would have to be taken with a grain of salt.
Paul, if I could add.
Yeah.
Experimentally research, we have some ideas about maybe taking the data close to the radar and trying to apply it at further ranges, vertical profile of reflectivity, some of those things that you probably heard about and they get down a little bit operational. So we would like to be able to extend it to where it's better application, but it's challenging.
So what's the distance range? 10, 15 miles?
I'd go further than that. I mean 50. Yeah, out to 50 is when, I mean, we see even weak EF1s can produce debris out to 50 miles. Not all of them, of course, but I've seen it out to 50 miles for EF1. So,
We're doing good in rainfall till it gets to the bright.
yeah,
So warm season rain, it's a long,
yeah,
further range, cold season gets closer.
yep.
Right now, you've got the different VCP, depending on, you know, what you're looking for and stuff like that. Is there gonna be that type of thing in dual pole that deals with the algorithms and also like tropical versus non-tropical rainfall, where you've got lots and lots of small drops?
Yeah, so you're asking about volume coverage patterns and if they're going to be modified for
Well,
dual polarization or more.
Yeah, and also probably onto that, you know, the ZR relationships change with tropical versus non-tropical in the current AD&D scheme.
Yeah, so dual polarization QPE products are still a work in progress. They seem to do best in deeper convection where the melting level is a long ways out there. And with KDP, KDP doesn't care what size the drops are. It's really measuring how much liquid is actually there. It gets you a better rain rate. So that's nice. So dual polarization products shouldn't depend on drop size distributions, whether it's tropical or continental.
This has been really helpful to go over the case studies, so thanks for that. But I'm curious, are any of the in real time, is any of the dual pole data available to us online?
Yeah, Betsy asked that. I'm a little disappointed that the Weather Service doesn't have it yet. And I'm not even sure when they're going to do it. It might be later this year at the earliest. But vendors, I mean, if you have I get it on my Android through, not that I'm plugging RadarScope, but I use RadarScope, and it's got the full suite of dual pole products for all the radars nationwide.
NonWeather has all the dual pole products also.
Okay.
If you're a Baron
Yep.
vendor, you can get it in your Baron systems, and Weather Central's 4.0 release of ESP Live will include all the dual pole product. No, I'm talking about ESP.
Yeah.
The radar. So yeah, that'll include the dual pole stuff also.
Is it extra cost?
No, it should be bundled in with your current base data too.
All those images I showed were Gibson Ridge. So if anyone has GR Analyst, you can get it that way too.
And your data source for that is
Uh,
storm scope, radar scope, right?
I get my level 2 data just from the free Iowa State site. Yeah.
But even the dual pole stuff comes through there?
Yeah. I mean, if a radar has dual pole on that craft site, the radar site, it'll be in there.
And was that GR2 or was that level, the 3 analyst?
That was level 2. Yeah.
The level 2 data has the variables, but none of the algorithms.
Yep. Yeah. Now, and I did hear he was making his own algorithms to kind of match it, but I haven't seen him yet.
There is also, I don't know if he's putting on GR3, do the level 3 dual pole output.
Yeah, it's in there though. These products are in the level 3 feed. So if you get a level 3 feed for any of the dual pole radars, it'll be in there. Okay, there you go. Yeah, which will be smoother, a little easier to interpret.
Well, I hope. I don't know about how all the different vendors are handling that.
That's true.
Same thing the 88D is doing, or have they?
Yeah.
experimented?
Yeah. Other questions? Yeah.
I was just wondering why you didn't use the KDP in the winter cases. It looks like, according to these charts, that it would be helpful in differentiating between heavy rain and heavy snow.
Yeah. So in KDP in winter precipitation, in my experience, just gets really noisy where you'll see pockets of higher, lower. I just never really saw the utility of using KDP there. Correlation coefficient, differential reflectivity kind of gets it almost everything you need. And so that's why I didn't really, it's such a noisy product, and I don't even know how to interpret it for winter weather. Even though it may say, I mean, a lot of those are based on research, and maybe we tweaked them a little bit. But for me, I'm not a fan of KDP in winter weather.
I totally see on-air possibilities for
Yeah.
correlation coefficient and KDP. Absolutely. I mean, the others, I think it would just be more off-air verification type
Yeah.
stuff.
Yeah, I mean, if you can show viewers, hey, this is debris, they get that.
It would mean something to them, right? I mean, my hope is that it would elicit such a strong reaction in them that, hey, it's saying there's debris, that they take cover.
Well, we had that Good Friday tornado and this pronounced debris ball.
Mm-hmm.
And I've never heard the Weather Service go off on debris balls
Yeah.
like that. And it got a strong response from people that all of a sudden we were using verbiage that they'd never heard before. Wow, that must be serious. And I would see us using a product like that, much like we do velocity, more often than not.
Mhm.
There are times when we have a little time to fill that we talk about inbound, outbound, but many times we'll just use the blotch and say that point right there is what we're watching. I don't have time to get into why. Just know that that's our focus right now. And in that way, operationally, obviously, it's very, very useful, but even visually on air.
Yeah, and I'm really confident inside of 50 miles roughly that the high-end tornadoes, you will see debris. There's almost no question in my mind. You will see debris from the high-end tornadoes.
And we've seen some extreme events, the supercells, debris signatures, over 50, 150 to 200 kilometers.
Yeah.
They have to be the big bad.
Yep. That tornado I showed in May had debris up to 43,000 feet off the ground.
That was an EF5.
And it was an EF5, yeah. And so Joplin, I bet any one of those would have had debris similar to that, had it been dual pole.
Now, research-wise, what would a product like that, what benefit might that have as somebody goes back and tries to determine how much debris was, and correlate that to uplift, and I don't know. I mean, it would seem like it would be pretty beneficial.
That's exactly what I just reviewed a paper from NSSL OU, and he looked at all those debris signatures to see, well, does it correlate to where the EF4, EF5 damage was, and the size of the debris, how low the correlation got. And it turns out that he did find a pretty good correlation. When correlation, gosh, I'm using correlation way too much. When the product correlation coefficient has a larger area and a much lower value, that corresponded to much severe damage at the ground. Now, it still doesn't give you lead time, but it's the same deal. You see that signature, you can get on the horn to your first responders saying there could have been an EF4, EF5 right here 5 minutes ago. Because roughly there's a 5 to 10 minute lag between when tornado does that damage and the product really decreases. But those first 5 to 10 minutes are crucial. You could send your crews right there to where the worst damage is thought to be.
And it certainly does give lead time to anybody downwind.
Oh, yeah. Yeah, if you can say that's probably an EF4, EF5, or at least damage characteristics of it, that would say something.
Those are first results, so you have to be
Right.
careful. Qualitatively, we can say it's bad. But
Yeah.
I just cringe at this, being able to look at just a little bit of data and say, oh,
Yeah.
that's EF4, EF5.
He needs to look outside of Oklahoma, too. All his cases are in Oklahoma. I just because whatever tornadoes churn up has a little bit different signatures.
David Bogey.
Yeah, it's his. Yep.
I'm impressed by how little it takes to create a debris signature.
Yeah. Little.
Math,
Mhm.
you